to the least squares regression line. So today we're also going to be covering how to find the equation, the model, the least squares regression line analytically. So there's two ways that you need to be able to find the least squares regression line. One of them is by looking at that computer printout like you've seen on your previous homeworks. They tell you the values of the y-intercept and the slope, as well as which variable is the response and which variable is the explanatory in that screenshot of there. Today we're going to look at how to utilize the summary statistics. Before we get there though, let's talk about a scatter plot. And if we have a scatter plot, we might get something that looks like this with the values x and y. It should be noted that the mean would be probably somewhere right around here for the y. The mean would be somewhere around there for the x. And if I did this, this would probably be the least squares regression line right here. Y equals a plus predicted, or y equals a plus bx. That's what the line would be because it is a line. That's how the line equation would look like for that scatter plot, roughly, right? And it should be noted here that the mean of x and the mean of y is always a coordinate that the regression line goes through. So the least squares regression line always goes through x bar, y bar, even if not an actual data point. And in reality, it's mostly most never is. So in other words, the mean does not, it's not technically a data point, but if there's one point that least squares regression line must go through there, is the mean of x's and the mean of y's. And that's because of the way the method is worked on. If you recall, I told you that the least squares regression line is, from its name, the least squares. When we talk about the z-scores, we want to make sure that we minimize those squared residual squared values. You know, it seems probably like, whoa, that's a lot to throw at. Mathematically speaking, in order to do that, one of the points must be the mean of x and mean of y. But there's also another reason. The least squares regression line is calculated based on z-scores. All right, it utilizes the z-scores. So what we're going to do, if we transform xy to zx, zy, we get the following. Now, of course, each one is going to be different depending on its scatter plot, but what we're going to do is for every single point, basically, for every single point, we're going to calculate its z-score, because every point is an actual data. So this is the z-scores of x and the z-scores of y. And if we do that, our new scatter plot based on what we have above would look something like this. And therefore, the least squares regression line for here would look like this. Now, what I've done is I've taken all of these points right here, and for every one of these points, I've calculated a z-score for in terms of its x. How many standard deviations is it away from the mean of x, and how many standard deviations is each point away from the mean of y. I would then calculate and plot those as coordinates. All right, And this equation, it turns out, for the regression line, is y equals y equals, oh, so that's not y, sorry, it's not y, that's what's throwing me off. It's zy, the z-scores of y, because that's the y-axis is zy, is equal to r times the z-score of x. So basically the y-intercept is 0, and the slope, if I were to calculate the slope here, it turns out to equal the correlation value, where r is the correlation. As such, in terms of a model, we can predict the z-score for y based on the correlation times the z-score of x. And this is a very important model or equation for us that we're going to use for here. So what this statement says is the following. We would expect the response variable, and notice I said expect because it's a model. That's the little hat. That's why we have that hat symbol. It's not that we would expect the response variable to be r, which is the correlation coefficient, times the z-score of x r times z of x, standard deviations from the mean of y. I'm going to clarify this. So basically it says this. Let's talk about example. Let's talk about two variables where x is equal to weight, and we'll say weight is in pounds, and y is equal to height, and we'll call that in inches. Okay. The correlation between these two values is 0.7. So it's moderate. It's moderate to strong. It's right on the border of moderate strong to strong between these two variables. Okay. So the best way I can explain it to you is the following. If someone is of average weight, what would you expect their height to be? Anybody? If someone is of average weight, so somebody's an average weight, so they're an average weight person, what would you expect their height to be? If you had to guess. And maybe you've been to those carnivals where they guess your weight, or they guess your weight and stuff like that. This is basically what they're doing. And we're just going to reverse here. If I could have said average height and then guess your weight. But if this person is of average weight, We don't know what the average weight is. If I had the variables, I could do the calculations. No, we don't know what the actual height is. That we don't actually know a number. All right, we don't know the actual number. There's no information here that tells you anything about an actual height. So you can't actually tell me the actual height, the number, the value. And also, I said it was in inches. But based on this question, just think about it in general. We know this person is his average weight. What would we expect about their height? Yeah, it would be average. Exactly. We would expect them to be of average height. So if somebody's average weight, you would expect them to be average height. So if they're average in one variable, you would expect, and so, if you know nothing about this person, and so here's the idea, you don't get to see this person, okay? You don't, if you don't know what a person looks like, but if I told you somebody was going to come into the room, somebody was entering the room, all right, and I said, guess their weight and guess their height. Okay, and that's what you had to do. You had to guess the weight and guess the height before you ever. And I said you can be off by a couple of inches. All right, it's okay to be off by a couple of inches. And if you can guess their average weight and their average height, what would you guess? And the answer is that you would guess the means. You would guess the mean of height and the mean of weight, because if we think about weight, and it's normally distributed, this is the mean of weight. And so if you wanted to guess, you'd want to guess here, because you know mathematically that the largest area, that if we take a little panel of the area, the largest area would occur right around the mean. So if you wanted to have your best chance to guess their weight, maybe within an inch or two, okay, you had a little wiggle room, and you had to guess their weight, you should guess the average, whatever the average weight is. Okay, so first off, you would have to calculate and get some data to calculate what the average weight is. But if you knew the average weight, that's what you would guess. Okay, I'm not actually putting a number here. And the same thing is true for height. If you wanted to guess, you would guess the average height for that person. And if you guess, and if you do this every single time, let's say there's 10 people that come into the room. Now, not everybody's going to be average weight and average height, but if you have no information, you have zero, you have no information about the person, and they're just walking into the room, then your best guess is always what the expected is. All right, I expect this person to be of average weight, because why? Because that's what they are most likely to be, or they're most likely to be close to somebody of average weight or of average height. All right, that's a very important concept. Now you can also do this, and this is actually also being done by the formula. It says that the predicted zy is equal to r times zx. Well, if somebody's average weight, what's the z-score for x then, if they're of average weight? If 0, perfect. So if I do that, I get predicted value equals r times 0. Now I didn't even throw in the correlation value, but any number 0.7 times 0 is 0. So I would expect them to be 0 standard deviations away from mean weight. Okay. B, if someone is 2 standard deviations below the mean in weight, well, actually, let me switch that up. In height, then what would you expect their weight to be? Now, first off, weight. Now, what I told you that the correlation, if x is weight and y is height, then the correlation is 0.7. Well, what happens if we flip it and now x is height and y is weight? What is the correlation? So I flip the variables, x and y. Instead of x being weight, x is now height and y is now weight. What is the new correlation coefficient? What is the new r? No. Anybody else want to take a shot? If I switch the variables, so now x is height and y is weight, what is r?
Wouldn't it be the same?
It is the same. It doesn't matter if you do x and y or y and x, correlation stays the same. So I was just trying to throw in a little review in there to make sure. Now what's important here is that they are positively correlated, meaning as one goes up, you would expect the other to go up. As one goes down, you would expect it to go down. So do you think this person is going to be, first off, above, knowing that there's a positive correlation, is the person going to be above or below average weight? Or what would you expect them to be? We don't know they are, right? They could be short, but stout, however you want to say it. So they could be. But what would you expect their weight to be if you have no other information about the person except that they're below the mean of average height? What would you expect about their weight? You don't even have to know statistics in here. This is just common sense. Below average, yeah. Below average. So Tyler, you got to make sure you say that below average, and make sure you get that part. So yeah, we would expect them to be below average. If they're shorter than the average person, you would expect them to be lighter than average as well, to weigh less than average as well. Now that's not always the case, but in terms of expectation, in terms of average, in terms of statistically speaking, we would expect them to be below. Now, how much below, right? So what I've told you here is that the z of x is 2. So sorry, is -2 because it's below. So if we utilize our formula, we get that the zy would be r times z of x, which is 0.7 times -2, which is -1.4. So we would expect them to be what? How do I interpret this z-score? I would expect them to be what? The next part of the material is much longer than this part, so we got to really get moving. I got 3 people so far that's helped participated. We don't know anything about what the actual values of the weights are. We just want to interpret this right here. Now I already did the hat part. I expect. Okay. Want to see another person chime in?
Should we expect them to be closer to the median?
Close is relative. So we got to use this number. We got to use this number. 1.4 standard deviations below the mean weight. So first off, it's y is the weight. So we're talking about weight here. So we got to make sure we say weight. Z-scores talk about average. All right. We can say the average weight or mean and average. So since the z-score is negative 1.4, the interpretation of this is 1.4 standard deviations below the mean. All right, because what really we're saying is z equals negative 1.4. And if you remember from those homeworks when we first started this unit, or even, no, sorry, this is unit 2, that z-score would be 1.4 standard deviations below the mean context of the problem. So we have to add context here. So what we found is negative 1.4. We would expect them to be 1.4 standard deviations below the mean. That's what we would expect if we had to take a guess. Now, if I had to guess an actual weight, I would have to do a little bit more mathematics, right? If I had to do the actual information, I'd have to know what is the mean weight, what is the mean height, what is the standard deviation of weight, and what is the standard deviation of height. If I have that, then I can calculate what 1.4 standard deviations below the mean actually is. We're not doing that as much here. The focus on this problem is just understanding in relations to how many standard deviations. If we only know standard deviations from the mean for one variable, we can only interpret or predict standard deviations in the other variable. If we knew x bar sx, y bar sy, we could predict actual values. All right, just want to point that out. All right. But what happens if I give you that one? So now let's talk about problems where I do give you that information. Finding the least squares regression line given summary stats. And now the summary stats for bivariant data are x bar, sx, y bar, sy, or mean standard deviations, and the correlation between these two variables. We should also note all least squares regression lines go through x bar, y bar. So formulas on formula sheet. So the following formulas are given on the formula sheet, okay? And you should have this readily available to you when you're doing this. It says that predicted y equals a plus bx. So this just tells you that the formula for a least squares regression line, it should be written as a plus bx, where a represents what? What does a represent? Oh, come on now. What does a represent?
Intercept.
The y-intercept, and b represents the
Slope.
Yeah, come on, guys. You guys gotta get it in. So A plus bx. You just need to know which letter, A or B, because we could write it as ax plus b, mx plus. So we need to know what letters we're using. So A represents the number by itself, which represents the y-intercept of the line, and B represents the slope. So that's the first equation that is given to you on the exam. Okay. Now, what is also given to you is how to find the slope. The formula for slope is R, the correlation, times the standard deviation of y divided by the standard deviation of x. And this actually comes based on this relationship right here. It actually is based off right here. So if you're wondering, like, why is that? There's a little bit more mathematics behind there, but that's what it is. If you know R, the standard deviation of S, and y, and the standard deviation of x, you can just plug them into this formula to find B. And the final formula is just the relationship. It says that the mean of y, which you know, is equal to A plus B times the mean of x. These are the three formulas that are given on your formula sheet. And once you found B, you can plug in B right into there. And you remember, you know what x bar is, and you know what y bar is, the mean of x and mean of y. And so you just plug them in, and then you solve for A. So you can use this relationship to solve for A. So find B, plug B x bar, y bar into formula, and find A. That's the whole process. All right, it's the same every time. It's literally, this is as formulaic, mathematically formulaic this course gets. So those three equations right there, really it's only these two equations. In reality, this is the main equation you need. As long as you have that equation right there, that it can be hard to memorize, you're good. But I usually want to have all three of them. So that's how you find slope. Slope is the correlation times the standard deviation of y over the standard deviation of x. Let's do an example. And yeah, we'll do an example, two examples technically. So here's the example. It's going to be a little bit of writing. I'm going to write it down, the context of the problem, and then then we'll actually do it. So a study found a correlation of 0.037 between a person's age and how much money is spent at a local store. Now that's a very weak correlation right there. There's a very weak linear relationship between, but there is some type of relationship, all right? And so if you're a shop owner, this is the type of things that a really good business person actually does. They want to find predictors. They want to be able to predict how their shoppers are going to be working. So they want them to spend more, right? You, as a business owner, you want to make more money. And this is how it's actually worked. So one of the things you might want to predict on is somebody's age. Now, there's a lot of other things, especially in the movements and stuff that's going on right now. Now, I do want to note that there is nothing that we're trying to point out in terms of being being racist or being biased or anything like that in terms of a person's age, race, gender, and stuff like that. We're not trying to point that out. In the world of statistics, the idea is that you try to disregard that information and you're just looking at the data. All right. Now, some people will interpret that differently. For example, on this one right here, what this model basically says, and it's a very weak, but there is a relationship, that the older somebody is, right? The older somebody is, the more money we would expect them to spend. And this is what happens, and this is what a lot of businesses are, and a lot of the businesses that grew and became billion-dollar industries understood this concepts and these relationships very early. All right. Now you get a lot of movies, for example, like Pretty Woman. It's pretty old. I don't even know if anybody knows that movie. Or other movies where somebody's young, right, and they go to a store and a person looks at them and they're like, oh, they're not going to spend much money, and then they go, ha ha, I really do. Okay, those are outliers. The idea here is you got to be okay with understanding that you might miss. It's not always going to be the truth, but it's an expected. So if you had to put your resources into something, you would put your resources into someone who is older, because the models that you have created state that you would expect them to spend more on average. Now, if it's just one individual, there's a lot of variance. But if you do this for hundreds, thousands, and millions of times, in the end, you will make the right decisions more often than you will not, and you will come out better on the other end. This is a general idea of how statistics work. All right. So same thing goes, but there's not just models for ages. They might mean something about how they dress, right? The more expensive somebody's clothing is, the more you would expect them to spend as well. And so that's one of that is actually things that they've behind the scenes, instead statisticians have done to actually maybe quantify how much more. So that's why they're directed at you see somebody that's dressed a little nicer or of a certain age. The reason why you are being more accommodating to these individuals, the reason why you give more resources to these people, is because, statistically speaking, on average, based on all your data that you have already collected about your store, those people spend more money on average. Okay, now there's a lot of other things that you have to take into account, especially in these day and ages, because nowadays you can get that canceled, right? Hashtag canceled stuff. So these days, just you make the wrong decision, or you do it incorrectly, or you do it in the wrong way, and all of a sudden it seems that there's other issues at hand, and you can end up losing money, marketing type of problems, right, in the end. So sometimes, especially in these day and ages, you have to adjust your statistics, and that's why statisticians get paid so much money, because there's things called risk. There's probabilities, as we're going to get into. If you do this too much, and you don't, this is why big companies do things like charities. This is why they do donations. This is, it's to protect the image type of thing, because if you only cater to one individual, now if you are correct and it's a really strong correlation, then it might not matter. But if it's only a little bit, like this correlation, you probably don't want to put a lot of resources in. So that's my spiel. Hopefully that makes sense in regards to just in the real world. Okay? The average shopper is 29.67 years old with a standard deviation of 8.51 years. The average shopper spends $572.52 with a standard deviation of $253.62. So in this problem, I've actually also given you the mean and standard deviation. Now, I want to point out that this information, along with this, is sometimes just presented as a table. And I think in almost all your homework problems, I think it's presented as a table. And it'll be like the mean, the standard deviation, age and spent. And let's see, so the average age is 29.67, 8.51 standard deviation, 572.52, and 253.62. Okay, so now if you're given this information, and then they might say, like R equals 0.037. Sometimes you're just given what I put in blue, all right? But the stem of the question gives you the context. Well, what does the context mean? Oh, the age is the age of a shopper. So we talk about age, we're talking about an age of a shopper at a local store. And when we say spent, spent refers to how much money they spend at that local store. All right. So you do need context and the problem still. So that's why there's all those words there. But if you look at it, mathematically speaking, all you need is what I just did right there in blue. Now, which is the x variable and which is the y variable? Anybody? Take a guess. What is the x variable? What is the y variable? What is x variable? Which one of these two variables is x?
Age.
Okay, you would think so, right? You would want to take somebody's age and you would want to predict the money spent. And if you had to do in real life, that's probably what's going to happen. All right, age would most likely be the explanatory variable x. However, nothing in this problem has stated it. The answer is that's a trick question. We don't know yet. That's the real answer for here. However, now I write find a linear model that predicts money spent based on age. Now predicts money spent. So now this is my y variable and this is my x variable. How do I know that? It's because the question. So you have to read into the question. And also this is question A. Okay. So now x bar is 29.67. Sx is 8 points. So now this tells me that x bar in this specific problem tells me that x bar is 29.67. Sx is 8.51. Y bar is 572.52. Sy is 253.62. And of course, R is 0.037. Okay? So, and I've stated right there, but I'll state it again. X is the age. Y is the spent. Okay. So, how do we do this problem? We just use those three formulas that I showed you in the previous problem. So we start off by writing out our main formula. Y bar equals, now I'm going to use Y bar now. Now notice because I've said age and spent, I don't need to write the context in here. I'm going to do it at the very end either way because I like doing it. A plus BX. Okay. Now, what do I find first? Now, remember, x and y stay in the formula. It's a model. It's an equation. So x and y stay there. So we need to find a and b. Which do I find first? Who can recall from earlier on? Which one do I find first? Which one do I have to find first? So look up in the notes. Somebody. Age is not one of the variables. Age is not one of the unknowns. X and Y, age and spent, are not things you find. This is finding the model. There are two unknowns here, A and B. When you do these, you need to find A and B. That's all you got to do is find A and B. So which one do we find first? A or B? Got 16 of you in here. I hope they're all here. I've gotten responses from 4 individuals total. Let's bring it in. I'm gonna have to start putting some more of a heavier grade on those that are actually responding during the time, if this is going to be the case. Which variable do we find first? Which unknown? A or B? Like I said, got to look up into here. It says right there. Find B. B is R times the standard deviation of Y over the standard deviation of X. So now we're going to utilize this equation. So now this gives me B equals 0.037 times the standard deviation of Y, which is, all I do is plug in. All this stuff is just plugging in over 8.51. When I plug that into my calculator, I get about 1.10. Okay, so this is one of the first equations. That's the second equation. The third equation says that y bar equals a plus bx. Okay, so now I'm going to take that information and I'm going to plug it in. 572.52 equals a plus 1.10 times 29.67. So I just plugged in to those formulas. So now that I can find A. All right. Doing that, multiplying and subtracting, you get A equals 539.88, which now gives me my model. My model is that money, I predict that the amount of money that they will spend based on age is predicted spent is equal to 539.88 plus 1.10 times their age. And that is their model, is the model. Now, I could have used y hat and x because I defined what y is and x. I defined what variables they are, but I like to always write my models using the context in them. B, find a linear model that predicts age based on how much money is spent. Now, something very important here. Do not try to solve for x in prior problem. So A lot of people, you know, when you did this in your algebra classes, you would be like, oh, well, if I know y is equal to this, then x is equal to that if I just solve for the other equation, right? If I just do the math, you know, subtract 539.88 and divide by 1.1 and I have an equation. No, that's not how it works. You have to redo the entire process because the least squares for x are not the same as the least squares for y. However, what all this tells me now, it tells me that the variables have switched. Okay, so now x is spent and y is age. So now x bar is 572.52 and sx is 253.62. Y bar is now 29.67 and sy is now 8.51 with r still being 0.037. So x's and y's switched places, and so now my x bar and y bar are the opposite values. So now we have 4 minutes left. Let's take and see what we've done, if we know how to find this. What is the first thing I write down on my paper now that I'm trying to solve this? What is the first thing I write down? Probably going to need to say it verbally. We got 4 minutes. You want me to be able to do this. You want to make sure you can do this. There's your homework. This will most likely be what you will have an exam question on this. So best to say something and be wrong about it and get it corrected now than just being silent and never understanding how to do it. What do I want to write down first? I'm going to show you over here. What am I going to write down first? You guys just don't want to speak today. Just the model, the general formula. Y hat equals a plus bx. That's always the first thing you want. What's the second thing I'm going to do? Find b. So I write down the equation for b. Sy over sx times r. So b equals 0.037 times 8.51 over 253.62. Doing that math out, I get b is 0.0012. What's the next thing I do?
Then find a.
And find a by plugging with the means, right? So y bar, the mean formula, a plus b x bar. So 29.67 equals a plus 0.0012 times 572.52. And that gives me a equals, when I do that math, it gives me 28.98. Now, I could also ask you to interpret, right? I can also ask you additional questions, like interpret A, right? So that just means that our model predicts that somebody who comes in a store and doesn't buy anything, doesn't spend any money, is about 20, I would expect them to be around 29 years old. They didn't spend any money. And if somebody comes in my store that's younger than 29, I would expect them to spend negative money. Ooh, I would expect them to steal. I guess that's the context of what you're saying. So predicted age is equal to 28.98 plus 0.0012 times money spent. Your homework is on Google Classroom. Thank you for those of you who participated. Those of you who are not, we need to pick it up. You cannot be successful if you're just watching and writing down only. We got to make sure that we're getting on top of everything as well. There's tutoring tonight in Pi R Squared with Mr. Chen, Tom Chen. I've sent him along the materials. If you did not understand how to do these problems, make sure you're going to those tutorings tonight. If you haven't signed up yet, You can still sign up. You can still just join, and then we'll get you signed up after that. Beyond that, see you tomorrow.